relational databases were never designed with big data in mind. In fact, the concept didn't even exist when they were first created. There are many ways in which a relational database will not satisfy the needs of today's applications, with scalability and overall performance perhaps the most daunting obstacles that can't be overcome. Since a highly dynamic industry such as information technology is continually evolving, it should come as no surprise that alternate solutions would quickly spring up to fill the gaps. As we're seeing in this video series, that's exactly what's taken place. In this video, we'll demonstrate the bottlenecks inherent in a relational database's join architecture. Later in the series, we'll show you how much easier those tasks are handled by more up-to-date technologies. Joining two tables to retrieve a consolidated record is a well-established, highly successful way of relating information in relational databases. In fact, if you were seeking to build a new application that did not need to deal with high volumes of unstructured data arriving very quickly in a big data environment, you could probably get away with using a relational database even now. But in a world where entirely new types of applications are continually being designed and deployed, relational databases are simply unable to keep up. This deficiency is magnified when considering the impact of many-to-many relationships, which are at the core of most modern applications. A social network is a great example of an application that did not exist when relational databases were designed. If you were to try to use the traditional relational database many-to-many approach for relating disparate objects in a social network, you will quickly discover that the computing complexity outstripped the relational database's engine capacity. To make things worse, the resulting database design would need to be altered as soon as new types of queries and relationships were required. Let's face it, the act of relating information between two tables is a computationally expensive activity, especially when the tables are large. In the use cases that have characterized traditional applications up to now, it was quite easy for the relational database engine to get away with this overhead. Essentially, increasing CPU speeds and new storage models have hidden the excessive work to carry out a join. But as new applications have come online, it's become apparent that relational database simply can't keep up with the overhead of many-to-many relationships. One way that developers have attempted to utilize their existing relational databases in support of new applications has been to apply indexes anywhere there is even a remote possibility of a join. But as we're about to see, that's just not realistic today. Indexing, however, is not a panacea. What these developers and analysts quickly realize is that over-indexing their databases immediately degrades performance while consuming massive amounts of storage. And meanwhile, the CPU and disk are still struggling to return results quickly enough. The intended goal of these indexing strategies is to reap their benefits for searching, while minimizing their overhead for inserts, updates, and deletes. But when all is said and done, the outcome is that relational databases, while extremely valuable and serving as core enterprise assets, are not the one-size-fits-all solution that they used to be. B-tree index searches are one example of where relational databases can get into trouble with the kinds of queries routinely found throughout big data environments. For example, let's suppose we're looking for someone with the last name of Keith. At the highest level, a B-tree index will typically split the last names in half as shown here. This node must be read first to establish which way to continue the search. Next, the A to L branch is split into equally sized halves, requiring another read. Further drilling down in the index now means examining the node that divides data for last names between E and G, and H and L. Now at last we're into the nodes that have a last name beginning with K, but our work isn't done yet. Finally, we arrive at the record in question. This relatively simple lookup took several reads, but it's important to note that in a true production big data database, we could be looking at hundreds of B-tree reads to find a single record. Multiply that by the cost of joins, which themselves need indexes, and you can see how costly even the most routine operations can become. As we describe in other videos, Flex Vertex uses indexes for identifying root objects and filtering results. But there's a big difference. Since the Flex Vertex data multiverse doesn't use joins, there's no need to go to the expense of creating and maintaining them. The upshot is greatly improved performance with vastly less overhead. We have plenty of other videos to help educate you on today's information management landscape. So remember to subscribe to this channel to be notified whenever we publish something new.